a crude oil pipeline 500 kilometers long with 400 millimeter outside diameter and 8 millimeter wall thickness is used to transport 600 cubic meter per hour of product from a crude oil terminal at San Jose to a refinery located at La Pos. Assuming the crude oil has a specific gravity of this and viscosity of 200 SSU at 20 degrees C, calculate the total pressure drop due to friction in the pipeline. If the maximum allowable operating pressure of the pipeline is limited to 10 megapascal, how many pump stations will be required to transport this volume? Assuming flat terrain, use the modified Colebrook's-White equation and assume a value of 0.05 millimeter for the absolute pipe roughness. The length of pipe is 500 kilometer. The outside diameter of the pipe is 400 millimeter. The thickness of the pipe is 8 millimeter. The flow rate of the pipe is 600 meter cube per hour. The specific gravity of the fluid is 0.895. The viscosity is 200 SSU at 200 degrees C. The maximum allowable operating pressure is 10 megapascal. The absolute pipe roughness is 0.05 millimeter. They say using modified Colebrook's equation. The modified Colebrook's equation is 1 all over square root of f equal to minus 20 log 10 E all over 3.7D E divided by 3.7D plus 2.825 divided by Reynold number square root of f. This is the modified Colebrook's-White equation. Now, from this equation, D, we need to calculate the internal diameter D. Internal diameter D is equal to the outer diameter minus 2 times the thickness of the pipe. Now, if you have a pipe like this, the internal diameter, which is D, will be equal to the outer diameter minus this thickness and this thickness. So it will be the outer diameter minus 2 of this thickness. So we have 400 millimeter minus 2 times 8 millimeter. So we have 400 millimeter minus 16 millimeter. This will give us 384 millimeter. So we've calculated the internal diameter. So the Reynold number, we need to calculate the Reynold number because now we have pipe roughness, the absolute pipe roughness E, the internal diameter D. We don't have F. We need to get our Reynold number. So Reynold number is same thing as density times velocity times internal diameter divided by absolute viscosity. Now kinematic viscosity is same thing as absolute viscosity divided by density of the fluid. Or if the kinematic viscosity is in Stoke, the absolute viscosity is in centipoise divided by the specific gravity. So with this relationship you can also get it. So now that means the Reynold number, we should represent it which is in this form, should now be substituting this value into this equation. Let's say it's into equation 1, let me call it equation 2. This should be equation 1. Into equation 2 you have Reynold number as velocity D divided by kinematic viscosity. Now from the formula to convert this kinematic viscosity, which is in 200 SSU to centipoise centistoke, we will now use the formula. Since this one is more than 100, now there are formulas to get your V in centistoke. You have 0.226 times XSU minus 195 divided by XXU when is within this range, within 32 and 100, when it's between 32 and 100. Now when it's more than 100, you have 0.220 times XXU minus 135 divided by XXU. So when this XSU is greater than 100, now that means we are going to use the second part of the equation. We're going to use the second part of the equation, so meaning that our kinematic viscosity will now be 0.220 times 200. Since 200 is more than 100, so we're going to use that equation, minus 135 all over 200. Now this will give us 43.325. Now we haven't gotten this is a centistoke. Now we needed to calculate the Reynold number. So the Reynold number, now before we do that, we don't know the velocity, so and we know the flow rate, and flow rate is equal to velocity times area. Area is equal to pi d square all over 4, and velocity, we have velocity as q all over a. If you substitute the formula for area into this equation, you now have 4q all over pi d square. Now substituting this, let me call this equation, I have equation 2, I have, this should be equation 3. So substituting this should be 3 now. This should be our 4. So substituting equation 4 into equation 3. So we have our Reynold number as 4q all over pi d square all over pi d square times c divided by kinematic viscosity. So we have now 4 pi, because this will cancel this. We have 4 pi all over pi the kinematic viscosity. So using this, you now have 4 times the flow rate is 600 meter cube per hour, divided by pi times 384 millimeter times 43.325 centistork. Then now that means we have 24,000 meter cube per hour. Now we needed to convert this hour to seconds. This hour to seconds. So 1 hour is equivalent to 3,600 seconds, divided by, you have pi times 384 millimeter. So to convert millimeter to meter, you have 1 meter equivalent to 1000 millimeter. Now to convert this centistork to feet square per second, so you have 1.076 times 10 raised to the minus 5 feet square per second all over, equal to 1 centistork. Now you have this hour, will cancel this, so we are left with 2,400 divided by 360 meter cube per second. Then the down one, you are left with pi times 384 divided by 1000 meter times 43.325 times 1 point, because this centistoke will cancel out the centistoke. 1.076 times 10 raised to power minus 5 feet square per second. Now this is meter, so we need to convert this feet square per second to meter per second, meter square per second. So 0.3048 meter is equivalent to 1 feet, so this will be squared. So that means this will cancel out this. Now we are left with 24,000 divided by 3,600 meter cube per second, divided by pi, times this should be 0.384 meter times 3.325 times 1.076 times 10 raised to power minus 5 times 0.3048 square. This will now be meter square per second. So with this times this will give you cubic meter per second. So this, it will cancel this one up here. So let's calculate this and see what we get. That means the Reynold number will be, let me get my calculator. I have 2400 divided by 3600 divided by pi divided by 0.384 divided by 43.325 divided by 1.076 exponential 5 negative divided by 0.3048 square. So we have Reynold number to me 12,760. So this is a turbulent flow. Now, having getting this, we can now find the friction factor using the modified Kolobuk's-White equation. So we will now use Excel. Let me pause the videos while the Excel is opening, the time it takes for the set to. So let me on the distance. So since the Excel has opened, now the absolute pipe roughness the internal diameter internal diameter of the pipe, okay. The Reynold number, the equation is a non-linear equation, the Colobrex equation. So I want to use Excel, GoSig. I'll use GoSig and solver to do it. Now the absolute pipe thickness is 0.05. This is in millimeter. The internal diameter is 384 millimeter. The Reynold number we got is 12760. Now we will now assume friction factor. Assume it to be 0.008. Let me make this thing to be big a little, so it will be visible. Now we have this, so we needed to use a formula. We need to create a function. Let me say a function that there is a constraint. So what we are going to use is, let me go back to this. We are going to use, this 1 all over the square root of the friction factor is equal to minus 2 log base 10 E all over 3.7 D plus 2.825 divided by Reynold number square root of F. Now adding this to both sides of the equation, this will be eliminated. So the equation will now be 1 all over square root of S plus 2 log base 10 all over 3.7D plus 2.825 divided by Reynold number divided by friction, the square root of friction factor. Now this should be equal to 0. So with this, we should now find the root of this equation, find the root of this equation, which is F. So the equation is a function of F, the friction factor. So we find the root where this equation is equal to 0. So that is what we're going to do using this Excel. So what we're going to type in here, before we do this typing, we define these things. Now I will define here, I'll go to formula, name manager. I'll click it, I'll just say new one. The absolute pipe roughness, I'll make it say E, give it value E. So I'll say okay. The new one, I'll call this internal diameter D. Then I'll select I'll select this B2, cell B2. I'll get another new one. I'll call this one Reynold number RE. I will select new cell, which is cell B3. I'll create a new one also. I'll call this F for go sake. So FG, let me say F underscore go sec for go sec. So now I will select this. Then I'll create another one. I'll call this F underscore solver. So I needed the F for solver, so I'll select here. I'll select this point for the assume friction factor for solver. Say okay. Now I will use the same value 0.08. So the solver now has the value. How's the value? This will be 0 2. Let me see. Okay. So now the function, which will be the same thing here too, now be equal to 1 divided by square root of f underscore go sec bracket close plus 2 times log base 10. We have e divided by bracket open and close. You have 3.7 times d plus 2.825 divided by bracket open and close. You have Reynold number times the square root of f underscore go sec bracket close. Bracket close. Then enter. Now I need to copy this. Sorry, I need to copy this formula. So the formula is there. So this, I'll change this. Change this to this. Change this to this. So same thing. Now for go sec, come here. I'll come here, select this. I'll go to data. Now I'll use this what if. Now for what if, you see the goal seek here. Now we set cell this equal to 0. Then here, by changing this value here, so I'll just say okay. So we'll have this is the real value for friction factor. Now let's use goal seek and use solver. Now you come here, select this, you select this solver here. You select this value of, so making the value 0, this value to be 0. Now you come here, you select the assumed friction factor, which is, they say, by changing variable cells, that is by changing this one. Now it's a non-linear. Now I'm going to adjust this to a more precision, a higher precision. This is, you know, this one, the goal seek has a precision of, this one has like 3 zeros, but this one now the precision is, okay, I'll call this one, the precision is 4. That is 0.0000. This at this point now is 0. Now this one has a precision of 1, 2, 3, 4, 5, 6. Now I can increase the precision here. That is why goal seek is better, based on accuracy is better. So now just click OK, and now say solve. See this is up to 9. The precision is 9 zeros. Why this is 4? This is 3 zeros. This should be 8 zeros. So the goal seek is of high precision. You see the value is a little bit different. So but at 4 decimal place, they will be of the same value. Let's see. So this is this at 4 decimal place, they are of the same value. So we are going to use this value, so we'll copy it, go into our calculator, we'll cancel all this, we'll just paste that value. Okay, 0.003. let me expand it again. Let me expand it. Let me now copy, let me see, paste. Okay, so that I will have more accurate value. Now let's go back to this. So we've gotten a friction factor to be 0.300936. Sorry, there should be 2 zeros here. There should be 2 zeros. It's okay, 0.03. Okay. Now, having gotten this, the head loss H will now be using Darcy-Weisbach equation. is friction factor times the pipe length divided by the internal diameter times velocity square divided by 2 times acceleration due to gravity. We know that V is the same thing as 4Q all over pi d square. Now substituting V equal to 4Q all over pi d square into this equation, you will now have this to be F times L over D times 4Q divided by pi d square all over 2G, this all squared. We have something like this: F times L over D times 16Q square divided by pi square d raised to power 4 2G. So invariably this will now be F times 8L Q square all over pi square G d raised to power 5. Now because this cancel, 2 cancel 2, 1, 2 cancel 8, 16 is 8. So this L times X, we get this. This D times D raised to power 4 is D raised to power 5. We have G here, we have pi square and all that. So let's work this thing out. So this phi is 0. This friction factor is 0.03000936 times 8 times 500 kilometer times 600 meter cube per hour square divided by pi square divided by 9.81 meter per second square divided by 384 millimeter raised to power 5. Now changing this to, now we have 0.03000936 times 8. Changing this kilometer to meter, you have 500 kilometer times 100 meter divided by so 1000 meter is equivalent to 1 kilometer. So this one will cancel out this. You now say this also is 600 meter cube per hour. Changing it to meter cube per second, you multiply this. So now this is 1 hour is equivalent to what? 36 seconds. See, all squared. You now divide, 3600 seconds, sorry. Now you now have pi square times 9.81 meter per second square times changing this 34 millimeter to meter. So you have 1 meter is equal to 1000 millimeter, or raised to power 5. Now we will now have this to be 0.0300936 times 8 times this should be 500,000 meter. This should be 1/6 meter cube per second square, divide by pi square times 9.81 meter per second square times this should be 0.384 meter raised to power 5. So the answer should be in this is meter raised to power 6 all over second square times meter, so that should give you meter raised to power 7 over second square. Then the denominator is meter square times meter raised to power 5, that is meter raised to power 6 per second square. So the denominator is meter raised to power 6 over second square. The numerator is meter raised to power 7 over second square. So this cancels out, it will only remain m up here. So the answer is in meter. So let's now work this thing out with our calculator. So we have now this value times 8 times 500,000. So 1/6 square will give you 1/36. So I will divide this by 36. Now I will divide the answer by pi square, so we have pi raised to power 2, then divide by this 9.81, divide by this value 0.384 raised to power 5 equal to this. So this is what we get. This is 4136.2. 4136.2. So what we got was 4136.2 meter. Okay, correct. Now we needed to change this to Pascal. Now you know which is pressure, which is the pressure loss. So the pressure loss is the same thing as saying the density of the fluid times G times the head loss. So we have the density of the fluid, which is the specific gravity 0.895 times the density of water. This is in kilogram per meter cube times 9.81 meter per second square times the head, which is 4136.2 meter. Now you can see if this acceleration, this meters, okay, let me now say this is 0.895 times 1000. The units will now be, this is kilogram times meters seconds. That is this, I'm using this to multiply this up here, divide by meter cube times 4136.2 meter. Okay, needed to times 9.81. So what I use the unit of this 9.81 to multiply this up here. So we have 0.895 times 1000. Let me bring this in back here, times 9.81. This one up here is Newton per meter cube, then times 4136.2 meter. So this, the final unit, if you multiply this meter with this, you have meter square. If you have multiply this meter with meter cube, that is this Newton divided by meter cube times meter. We have what you have now is Newton per meter square, so which is per Pascal. So you have this times this times this times this. Let's work it out. So we'll have this times acceleration due to times specific gravity, which is 0.895 times 1000 times 9.81. So we have, so answer now will be 36 316 066 066. Okay, 066.5 Newton per meter square. So this is saying this Newton is Pascal. So you have, so our answer now will be 36.32 megapascal. So this is what we'll get. Now they now ask us what is, how many, you see, how many pump stations will be required to transport this volume. Now, since the maximum allowable operating pressure of the pipeline is 10 megapascal, now if you want to work against this pressure here now along that pipe, it will not be possible. The pipe will explode at this 36.232. So for us to meet up, let me just say, for instance, you have the pipe. This is a pipe. So here is 500 kilometer. Now, and you needed to overcome friction loss of 36.32 megapascal. Now, but this pipe, the pressure on this pipe should not exceed 10 megapascal, meaning that we are going to need, for us to overcome this, we are going to need the number of pump station will now be equal to the friction factor, the friction loss, which is 36.32 megapascal, divided by this value. So this will give us 3.6, which is approximately 4. So 4 pump stations, meaning that